Right, line P3, learning task number 6. Now we're going to go and take a look at three-phase instrument transformer connections, describing them, describing what they're going to do and how we're going to connect them into purposes, and then later on we're going to go and take a look at a bunch of the calculations that are associated with these. We're going to start by talking about PTs, and PTs are also sometimes going to be called VTs. PT or VT stands for potential transformer or voltage transformer. And they're going to be a special type of precision transformer that, based upon the high side voltage that you go and place in, so they come inside of a range of high side voltages, you are always going to go and have a low side voltage of 120 volts. That's going to come back out of these things. This allows us to use standardized equipment when it comes to our measurement, particularly when we're looking at something that's a ridiculously high value of voltage. It just makes sense to knock it down to 120 volts where we're going to be able to meter everything, relatively simply and relatively safely. Over here, they're showing us a PT connection that we are going to go and have. And where you might see something like this is if you had a place where your high voltage was going to be, let's say in this case, it's going to be a 25 kV. 25/14.4 kV system, meaning that it's going to be 14,000 volts going across from any one of my lines out to the actual neutral itself, and then 25,000 volts from line to line. What we see over here is that we have got a Y to Y type of connection, where on my high side over here, I'm connecting as a Y over to the neutral, and then to my individual lines, A, B, and C, as we go along there. And then I see on the low side over here that my low side is going to go and have a rating of 120 volts. In other words, when this rating right over here receives a full 14.4 kV, this one over here is going to go and receive a full 120 volts. And if for whatever reason the high voltage phase winding would drop in volts, a surge or a drop on the system, then my low voltage one would as well. So we're able to go and transfer just a scaled down reading all the way through. If I take a look at my low voltage side is going to be connected in a Y type of configuration as well, A, B, C, and then I connect a star point, and you can see that there's a neutral that's going to be connected to this one here as well. This allows me to go and take individual phase readings, A to neutral. It's going to be scaled down from this one over here through the transformer ratio down to this one as well. So we've placed 3 individual voltmeter sections inside of there that are then going to go and give me volts that I'm going to go and have out. These are going to be phase values of voltage that we have over here as well, because I note that this is my star point going across here, here, and here, which means that from this, the star to an outside leg is just looking at a phase value. Other times we're going to go and use our PTs when we have got only line-to-line values of voltage. So if we have got something now where we had the same system, 25 kV, but now it is a delta type of system, I'm going to go and have 25,000 volts that is going to go across here. I cannot be using the same PTs as in the previous one, because in the previous one, the voltage that was actually across the high side here was 14.4. Now the voltage that's going to be across the high side is going to be 25,000. And I see that my high side is going to be connected inside of a delta type of configuration, A, B, and C. This first transformer, it goes all the way across from line A to line B. Then line B goes across to line C. Then line C goes back across to line A. On my secondary side, I see that I'm going to go and have now my voltmeters that are going to be connected across as, once again, a Y type of connection over here. So I'm going to go draw that Y type of connection out over here. Remember, we're going to have a 30-degree phase shift as soon as we go from delta over to Y. And I'm going to have my A, B, and C that I'm going to go and have over here. And then this star point over here is now going to be carried across to there. Now, if I take a look at my transformers, whatever I have on my A phase over here, my high, I'm going across from A to B. I'm now going to go and see that as a phase over here on my secondary side. So my voltages that I'm measuring are A to B. It says A to B over here, but it's actually going to go and be A to N that we are measuring over here. And if we really wanted to go and measure the actual voltage that we had line to line going across, we would actually have to go and connect these PTs into a delta type of configuration where I would go from my A over to the B, etc. I'm just going to draw that over top to show you a true line-to-line measurement. Once again, it's just a small error inside of the book itself, but that's all right. We'll just address them as we go along. If I wanted to connect this thing as a delta type, I would come off of this line over here and then connect over to my B. It then goes through. Here's my transformer. Make a connection from here over to the next one to my C. And then from here, I would go back across to my first one. And at this point, you should be able to trace that through and see that we have got a set of delta connections. A connects across to B, B connects across to C, C connects back across to A. And then if I were to be trying to measure my values of voltage, where my meters are at this point would be perfectly fine, because right now I would be measuring across from my A to my B. I see up top, this one is A to B. Down here, this is going to be an A to B winding down here. We would want to go and remove this line over here if we wanted to do the actual delta type of configuration here. But that would get me, in that case, a true line-to-line value of voltage. All right, moving on past that, the next thing we're going to talk about is CTs. CTs are current transformers that are designed to go and, in most cases, clamp around the line or be bolted into the line. And then they're going to knock down the current into a smaller value. Now, because the current is going to a small value, that means that the voltage is actually going to have to go to a large value. You know, remember that whole VAN is equal to VA out. So we do have a higher value of voltage across these things that you have to watch out for, but the current is always going to max out at 5 amps. In other words, if I have got a 400 amp system over here, that 400 amp system, we're going to go and have a bus bar that's going to be passing the current through out to my load. So my load down here is pulling current through there, and then I would just have a 400 to 5 transformer over here. CT. By the way, CTs are always going to be rated, you know, the current to a 5. We're not going to go and say that it would be an 80 to 1, even though this is an 80 to 1 ratio over here. We would call it 400 to 5 that we have. As long as I'm putting current through this thing, I'm going to go and get up to 5 amps out. If I put out 50% of the current, so if I only put 200 amps through it, I would only get half of my 5 amps, so I would be getting 2.5 amps out of it, etc. Bring it all the way up to the 400 amp, and I would get all the way up to 5 amps out of these. They are going to go and allow us, once again, to go and create measurements safely. Even though, you know, we're measuring a large amount of current, 400 amps at this point, we could do this so with a 5 amp ammeter, which is good because a lot of our tiny little meter movements cannot handle a whole pile of current. Taking a look at my connection over here, I see that my connection is once again going to go and be in a Y type of connection. Looking at these over here, I see that I am going to go and have each of these CTs that is connecting across, and we've got a central type of line over here, and then that my actual ammeter itself is connected across as if it were across like that. We're going to have an ammeter there, we're going to go and have another ammeter here, we're going to go and have another ammeter that's going to be going across here. And it's just measuring the amount of circulating current that is going through that winding based upon whatever the load itself over here is going to be drawing through the system. There is this big important note over here. We have iterated this inside of second year, first year, third year, fourth year. We're going to keep talking about it until you're a journey person because it is so critical, and that is never open the secondary of a CT, because if you open the secondary of a CT, you are going to go and once again have that hysteresis. You're going to go and drive this thing hard into saturation, and then you're going to really, really quickly drop it back through in the opposite direction, which is going to go and induce a very, very large value of voltage across here. Really dangerous. We don't want to go and see that. CT transformers for measuring delta phase currents. Sorry, I should go back to this one over here. If you are going to take a CT out and it has to be on a live system, what you're going to do is you're actually going to short across. This is not a load transformer, this is a measurement transformer. In other words, the load over here controls the amount of current going through the main lines, which in turn controls the amount of current generated through here. You can place a shorting bar across here because you're guaranteed that at no point is there ever going to be more than 5 amps that's going to go and flow through this little loop over here. And at that point, once that's shorted out, you can safely go and detach your ammeter from it. But just never detach that ammeter while it is live. That would be critical faults, and we want to try and avoid that. Rolling back into this one, CTs for measuring delta phase currents over here. If I want, I can also go and take my CTs and I can use them to measure load. So over here, now we have gone into the actual load section. That's going to be these ones right over here. And I have inserted one of these into each load. Do note that I've got my polarity dots that are highlighted to line up. I'm highlighting this one to line up with B. I'm highlighting this one to go and line up with A. I'm highlighting this one here to go and line up with my C line over here. It's that node over there. We do maintain polarity all the way around because if I flip one of these CTs around, we're going to get false readings. So make sure that just treat these dots as if they were arrowheads, that we've always got an arrowhead going through, and going through like that. All right, let's erase those arrows real quick. Talk about the actual connection. Looking at my ammeters here once again, my ammeters are placed onto a delta connected load. That's these three blue highlighted things. But then the actual metering itself is going to go and be connected into a Y type of configuration. And this doesn't make any difference to us that this is connected into a Y type of configuration, because if I take a look at the individual meter loop, the individual meter loop is just reading what's inside of here. And we're not even looking at voltage. Voltage is the thing that changes around from, line to, from delta to Y when we're going across. This, at this point, we're just looking at current that's going through these. The only reason that we're making this connection like this is because it is intrinsically safer for us to go and do so. Now, I do want to go and note one other thing inside of this drawing, and that is the way that this delta connection, that we have all of these that are lined up. If I take a look, these dots lined up, these dots lined up, and these dots are lined up. There is another error inside of here, and that error is on one of my connections for this Y point over here. If you take a look at the Y points, what we should have is we should have the same line of each of my CTs connected. Take a look. Here's the dots, and then the tail end connects to my Y point. Here's the dots. The tail end connects to my Y point. Here's the dots, and oh my goodness, it's the dot end that's connected. This is a wrong connection. Ixnay that one. And it should be the tail end over here that is going to be the actual connection. Make that correction inside of your book. Okay, so those are our actual ammeters inside of there. We've looked just strictly at voltmeters, PTs, or VTs, whatever you want to call them, and we've looked at ammeters over here, CTs. Now what we're going to do is we're going to combine them both into the same system in order to go and form what we refer to as being a wattmeter, or a total amount of power that we are going to go and have. Now, we did take a look earlier on inside of our first line there, A5, we started to look at measuring power inside of a three-phase circuit. That worked when we had a balanced three-phase circuit. And I just want to go and point out that for that one, we always needed to go and have, we could get away with, we could either do the 2 watt meter method or we could do the 3 watt meter method on a balanced type of circuit. However, when it comes to actual revenue metering, what BC Hydro is doing, where they're tracking all of the power that's being used by a customer, you are not going to go and have a balanced load. It's just not the way it happens, because guaranteed there's going to be an extra 2 lights over here and then maybe a heater across this one, and so you're always going to end up with an unbalanced load. So what they want to do is they want to go and measure all of the power that is going to go and end up going through our system. 2 separate ways that we can do that, depending on whether we are delta or whether we are Y. First thing I want to do is I want to just go up top over here and I want to count the number of active lines from the source. I see that I've got 4 active lines, and what I can do is I can go the number of active lines minus 1, which tells me that I need to have 3 wattmeter elements. And what a wattmeter element is a wattmeter element is a VT and a CT that is going to be connected. In other words, when I'm looking at this, here's my 1 wattmeter. My wattmeter needs to go and have a VT. It needs to go and have its potential, as well as it needs to go and have its current that is going to be associated with it. If we take a look, I see that there's 3 PTs across here, and I see that there's 3 CTs that are going to be across here. So PT and CT, PT and CT, PT and CT means that we have got 3 watt elements for these. 4-wire system, 3 watt elements. We're going to go into the connections in a second, but I'm just going to jump ahead over here to my next one. My next one is going to be a delta system where I've got 3 lines. -1 tells me that I need to go and have 2 watt elements. And once again, if I take a look, I see 2 watt meters over here, but I see that I'm going to go and have now, as far as my elements, 2 VTs over here and 2 CTs over here. On this one here, by the way, I highlighted the wrong one. Let me just erase that one a second. This is the actual CTs. I highlighted the ammeters, just getting ahead of myself. Okay, let's talk about the actual connections that we are going to go and have on here. And I'm going to go and draw out my source just as if it were a very large delta type of, a large Y type of object. So I'm just going to pick this one up here, move this one down just a little ways over here, and then I'm going to go and draw out a standard Y type of system. A to neutral, B to neutral, and C to neutral is what I've got. And then this over here is going to go and be my neutral point. I'm just going to extend that little line out so we've got something to grab onto. Taking a look at what I have over here, I'm going to go and see that I'm going from my A, I have got a VT, or a potential transformer, that connects across to a small neutral that it's going to go and have. And you'll note that this neutral is connected to H2, is connected to H2, is connected to my main neutral. So what I'm actually seeing is I am seeing my transformer connected across from my line A. PT is connecting across to my neutral, like that. On the other side of this same transformer, this is going to be my A line over here, I'm going to go and see that I am going to go and establish another smaller system. And this smaller system, I'm just going to highlight the entire line, is going to go and form a complete loop over here. We've got what we call our voltage elements, and we've got what we call our current elements inside of a watt meter. So looking at this, I see that I've got that line. We'll extend the rest out here in a second. I see that this connects into here. I see that this connects into here. And then I see that this now connects down to here. And what I have across here is really just a connection that is going to go up to here. This is my voltmeter connection right over there. Those 2 lines like that we are going to go and have. So if I take a look at it, I see that this voltmeter VA to N is being measured across this red loop that we have over here. We'll just draw that one in like that. So we see that we have got a VA to N. I've got my 1 attached to line A. I'm going to have my 1 attached to my line A over here. And so this now goes down to a watt meter. Stick it into one side of the watt meter, as well as this has got the VA to N voltmeter that is going to be placed across it. So I can see the volts across it, as well as I can feed it into my watt meter elements. So we'll just stick that there as being our watt meter. Okay, so we're going to feed the voltage into the watt meter as well as into there. So I've got 2 voltmeters basically that are on the system now. Next thing we're going to do is we're going to take a look at our A phase. We're going to follow it along here once again, and we see that we have got a CT now that is going to go and be connected not in parallel the way that this one was, but I'm going to go and have a CT that's actually going to be connected around the line. So we're going to go and do that over here. That's going to be my CT. I see that I've got the dotted end connected over to the A, so we're just going to make that connection over there. And then I see that if I trace this down over here, that I am going to go through my watt meter. That's the ammeter section of the watt meter. And then it's going to go and come back, go through another ammeter, and then it is going to go and tie back down to what we would refer to as our common or a Y point for that system. Going through and drawing that out as that applies to this, we see that this is going to go and travel from here down through the watt meter elements. I'm just going to go and actually, let me just draw this watt meter much larger. It would make our life a whole lot easier. We'll draw the watt meter as a giant box over here. And the watt meter is going to go and have 2 sections. It's going to go and have a voltmeter section. It's got 2 connections, and it's going to go and have an ammeter section. amps and volts. It's got its two connections, and then inside of the watt meter, it combines those two readings of volts and amps to go and form our watts, like that. So I'll just go and finish up our lines over here. So going through this one, coming from our CT, from the dotted part of the CT, we see that we head directly into the watt meter. So we're just going to go and carry that all the way around here. We're going to go and head into the watt meter on the dotted side of our watt meter. That's connected. If you take a look, you see there's a little polarity mark down there. I'm then heading through that ammeter section of my watt meter and then back out where I've got another external ammeter, IA, and then from that IA, I connect all the rest of the way back up to the other side of that CT. We'll just kind of jump all the way around the outside like that. And then the voltmeter, we'll just finish that connection there as well. The voltmeter, we said, had a connection going from its PT, the low voltage side of its PT. It was coming into the watt meter. So it has got its own little section there and its own little section there, volts and volts. So when you're taking a look at this, and we're only going to draw out the A phase here right now. When you take a look at it, you'll note that we have got voltage measured in parallel across here. Current, we're passing it right through the primary of our CT over here. So we're going to be measuring our current in series. So our current just gets knocked down in series and passed through. We have an ammeter section with an ammeter section of the actual watt meter, and then an external ammeter so we can read it outside of the actual meter. Same with my volts. I can read my volts external as well as I can read the combined volts and amps together to go and form my watts that I'm going to go and have. All the rest of these connections are going to go and follow the same sort of configuration. Connections do look good on this page. There's nothing wrong with them. If you follow out the rest of the connections that are on here, you're going to find out that your voltmeters are all going to be connected into a Y type of system. And that doesn't matter. That just means that we're grounding one type of the system, or grounding one section, and that's really just a safety thing because each of the current loops still is going to follow the same sort of, where it loops through its own voltage sections. So the volts are going to go and have a Y type of connection. The amps are also going to go and have a Y type of a connection. Once again, we're just making that connection for safety inside of there. We're going to talk about the actual watt meter multiplier and how we arrive at that later on, but what a watt meter multiplier is it's going to be the sticker you see on top of your BC Hydro meters when you go into commercial or industrial premises. Oftentimes you'll see like X80 or something like that, and X80 just means that it is a times 80 multiplier that they're going to use for the meter. If the meter reads 100 watts, you're going to multiply that by 80 to go and read that as being 8,000 kilowatt hours there. It's just a ratio of this PT ratio multiplied by our CT ratio, and that's going to go and give me what my watt meter multiplier is, and then I just go and take those watts that I read off the watt meter and I multiply them by that multiplier to get to the actual true watts on the system. Okay, moving across now to take a look at our delta type of system. Delta type of system over here, we said that we had 3 lines. -1 tells us we need to have 2 watt meter elements for this thing, which we see. We've got PT and PT and CT and CT, and then CT and PT both are going to go and feed into our watt meters. Let's take a look at just one of these. It does not matter which one we look at, but we're just going to follow those connections through once again. We have 3-phase lines in here. We are going to go and carry in from A over to B on that delta type of system that we have. I'm actually just going to move this drawing over once again so that we can rerun this one the same way that the other one was. I'll put that one right there. Okay, and then we'll erase that. So here's my delta type of system. A to B, B to C, C to A. So I see that going from my A to B phase of my actual system itself, I see that I've got a voltmeter section that is going to be placed across it. And it's going to be a voltmeter section that will be made up of a actual VT or a PT, whichever one you want to go and call it. I'm tapping off on line A, and then I'm going over to that voltmeter high voltage section, then going across to my line B. And I see that on my A, I've got my 1 attached to it, my H1 section over there. Then I see that on the secondary side, I'm going to go and have a smaller, we're knocking this thing down from a higher voltage to a lower voltage of 120 volts. And if I go and follow my secondary side through, we are going to go from here all the way down, and we're going to go and enter into our watt meter, get measured by the voltage section, and then we are going to go and leave from the watt meter and come back up to this point over here, which we know is going to be grounded in between these two here. So I'm going to just go and do that down here. We'll draw out a larger watt meter once again. We'll call this volts, we'll call this amps, and I'm going to go and take my line from A here. This is going to be my line from A, and I'm going to go and bring that into my voltmeter section down here. It's going to pass through the meter, and then it is going to come back out of that meter, and it is going to go back up to the, take it around to the outside, opposite side like that. So we see that whatever I have for voltage that is going to be on this phase, we are going to go and transform that voltage down from whatever value it is down into no more than 120 volts using this system over here. There is another voltmeter that's being placed across here. It's just going to be my voltmeter A to B over here, and that's completely fine. It's just going to give us an external reading from outside of that watt meter that's combining it. Taking a look at my CTs, I see that my CT is being connected. It is connected. The primary to CT goes in line with my actual lines going out to the load there. So I'm going to go from here, and I'm once again going to go and follow this thing down. I'm going to go through the ammeter section of the watt meter, and then I'm going to go through another external ammeter, and then I'm going to go back up from this external ammeter through another meter, we'll talk about that in a minute, and all the way back up to my load itself over here. Let's just go and do that one. We've got our metering section, which is now going to be placed around here. Dot goes out to the front over here. And from there, we are going to go and feed out a line. I'm just going to pick a gray line for this one. A line that is going to go down, feed into the ammeter section. There's the ammeter section. Come back out of the ammeter section, feed into an external ammeter. And then it is going to go and feed through another external ammeter. We're going to come back to that one in a minute and go return over here. We see that both of these are complete circuits. My PT as well as my CT are going to go and be complete circuits where we can go and just run current all the way through these things. And they need to be complete. There shouldn't be any switching or anything inside there. We do see a couple of these fuses over here on my high voltage side, but that's just there for protection from, if we have any sort of a fault on there, because it's a high voltage type of installation. On my CT, you don't see any protection because the CT secondary should never be open, and whether that would open from an electrician doing stuff stupidly or whether it would open from a blown fuse, it would be catastrophic to our actual system. So we just don't want to go and see that. If we take a look at our connection that we have up top over here, you should note that we have seen that connection before where we've got two units that go across. One goes A to B, the next will go across from B to C. You should recognize this as being my open delta type of configuration, where I've got this one over here, we'll call that one our A, going across from A to B, and then I've got this one over here, we'll call that our B, going across from B to C. And because I've got those on my high voltage side, I'm going to go and have smaller ones that are going to be associated on my low voltage side as well, that are going to be following in parallel. That's what these ones are down here on the bottom, are the low voltage windings that we would go and see in parallel. If I take a look at my secondaries that I have down here, I should note a couple of things as well. Once again, these two, if I look at these lines, I'm just going to move them down over here. They're going to be connected together, but then I'm going to go and do this thing where I'm going to go and do what's called a corner ground on this system. And it is a corner ground that is just placed in there for safety. Just because we have created a new safety or a new system, we do want to go and have some grounding in place, because without grounding, it's impossible to go and trip out or dissipate a lot of our fault current. This is just a corner grounded delta, and this is the first time that we've been introduced to it inside of our units over here. It's still a delta system because I can see that going across the middle over here, I just have that ghost phase, and I'm actually going to be measuring this as my A to B, this is my B to C, and then this is going to be my C to A that I'm going to be measuring across that one over there, and that's done with this one over here. It's a corner grounded delta system that we have over there. If we take a look at our primaries over here, my primaries are my CTs. My CTs are connected together and once again going to be tied into the same sort of a system over here. I see that I've got my A that's tied in. I see I've got my B that's tied in. And then right over there that we have got that tap that is going to be tying these things into a corner ground here. What we're getting out of this corner ground here is just going to be our point where we feed all the way back through. Now we have this IB here. Let's talk about that for a second. IB is going to be the current that is inside of phase B. We know what our current is going to be inside of phase A because we're going to actually read it through this whole loop over here. And if I were to go and erase that loop, I could go and trace out my IC phase very similarly, and I'm just going to do that real quick over here. IC is going to go and travel through here, down through my watt meter, through its C element, and back up through IB. Wait a minute, did you see what just happened over there? What happened is that that current went through the same path. Let's just draw this over here. This is my A. A goes through its ammeter section, A goes only through the A meter, and then A joins in over here, and for a little bit of time, all of a sudden, there's two currents that are joined together, and then right over here, A is going to split back off and complete its circuit over there. This is simply going to go and be doing some phasor addition. It's a meter, it doesn't know that it's doing that, but it is going to go and read the net sum of my A current and my C current because we know that all the currents should go and balance out. In other words, if I have got current coming in on A and C right now, I would therefore have to have current coming out on B. And so we'd be able to read that with the A and the C, and we would get the same amount of current coming out through B. It's going to be the sum of those two currents. This is always going to go and work out for us, and you just really need to recognize it as the fact that we've got two separate currents, we split them, measure them individually, split them, measure them individually, and then we combine both currents back together, run them both through another ammeter that's going to combine them, and then back out to the load. It's actually pretty cool. The other thing that we have to talk about is just the direction of the watt meter reading. Now we have had a formula that we've looked at before, and that was that TAN formula. It's on the bottom of your page 112 there as well. That formula only works when we have got balanced loads. We cannot use it for general day-to-day loads. If we don't know if it's balanced, we have to go with the assumption that it's not, so we cannot go and trust it. Only use that if you know that it is going to go and be trusted, or that if you've got an actual balanced one. At times, you can also go and have your watt meters that are going to go and get reversed. One of these that's going to go and try and read downscale. If you do get a downscale reading, that just means that you've got a real crap power factor. First of all, I wouldn't even bother trying to fix the watt meter. Quite honestly, you're going to be below a 50% power factor. Fix the freaking power factor first, people. Then worry about looking at the meter. But if for whatever reason you can't fix that power factor, then go and flip around one of these two coils. Either you flip the connections on these two around, or you would flip the connections on these two around, and that would bring these things together. But you would have to go and subtract the readings of the one that was going downscale that you flipped around. You'd have to subtract it from the other. Once again, don't use that formula unless you know for a fact that it is a balanced type of load. CTs are also ridiculously useful for us if we have got large values of current that we need to go and track for other purposes other than revenue metering. One of the big ones is for when we want to go and monitor for overloads or things like that, and we'll do that often inside of motors. Now, if I have got a 1,000 horse motor, and yes, the motors that size do exist, those motors are going to have a gigantic amount of current that is going to go and run into them. And we would not want to go and place in overload heaters. You should remember what an overload heater is from your second year motor control. An overload heater is literally something that is designed to go and dissipate heat. The more current that travels through this overload here, the more heat it's going to dissipate. We'll place one of these on each of our lines. And we can go and dissipate heat, and what that heat is going to do is that heat is going to go and affect something. I'm going to go and just draw this here as a circuit breaker, but it's going to go and affect something. It's going to cause something to trip, which will then go and trip out the actual coil that is energizing your motor. So if the motor is working too hard, so we're going to draw some heat coming off the motor over here. So working too hard right now, it's going to be drawing too much current, which is going to cause too much heat at the overload heater, which is going to go and trip the little thermal element that is inside of that overload itself, which in turn is going to go and open up or kick out my coil. Usually this whole section, the overload heater and the thermal element, we usually inside of motor control combine it to just look like this. A normally closed contact, and we'll just label that OL, and that means that we've got a heater and the thermal element that's inside of it. Now, if it's a 500 amp motor, we don't want to be taking a 500 amp heater. First of all, it would be gigantic. Secondly, we would have a ton of heat that we'd be putting off of it all the time. So what we'll do is we will just go and get a CT. And this CT over here, if this one is a 500 to 5 CT, for every 500 amps of current goes through, it's only going to be putting out no more than 5 amps. So I would go and have a 5 amp overload heater over here that I would be able to go and place on there. Tiny, tiny little bit of heat that's going to come off of this thing, as well as it's going to be a small, cheap component for me to go and operate. Do note as well that this is the heater. This contact never opens. We've talked about the fact before that the CT should never be opened. My CT circuit in here will never be open because this overload itself, this is not the actual relay, this is the overload heater that's inside here. The overload heater is nothing more than a resistor. It does not have any switching elements. It's a resistor that gets hotter with more current through it, which eventually causes the actual overload element to go and trip out. The other reason that we'll go and use a lot of our instrument transformers is we're going to use them for ground fault detection. We are going to go and take a look at some ground fault detection when we go into some of our grounding and bonding systems later on, and we'll go through it a little bit more in depth at that point. But we will go and have lights that we're going to go and place across 3 of our individual lines, when we want to go and measure for any sort of a ground fault. In some cases, that works out fine when we have got things like a 600 volt system. Perfect. I can go and get lights that are going to be rated up to 600 volts, as well as they're going to operate at 347. Normally, if there's no ground on the line, all of these are going to be operating at 347 volts. But then if there is a fault on the line, one of these is going to go dark and the other 2 are going to go brighter because their voltage is going to go and change to 600 volts. We've explained this before inside of just our beginning section, line A5. We're going to explain it much more in depth later on. For now, just go and work off of that memorization, the fact that the 2 lights that got brighter are on the good line. The light that went out is on the bad line itself. The line is still active. The line isn't out. Just the light itself is going to go and be out. Little lights like this work when we have got a fixed amount of voltage. That is a controllable amount of voltage. But there's going to be times where we go to higher values of voltage. And sometimes in those higher values of voltage, we're not going to be able to go and, let me see if I have one. I don't. Yeah, here we have. At other times when we go into high voltage circuits, we're not going to be able to put the lights directly across. So we're actually going to have to step down through the use of our PTs down to a smaller voltage level. Looking at what we had here for ground fault detection, it was just operating off the fact that normally speaking, we've talked about this a number of times, on a delta type of system. I'm just going to move this one here. Normally speaking, on a delta system, give me a sec here to erase this. Where's the neutral on a delta system? That's a good question, isn't it? We've talked about this before, that there is no neutral connection, but we know that it exists in the center. All the voltages are going to be inherently balanced around that point over there. And so what we have over here is we've got that same delta system, and we are going to go and have a couple of lights that are going to be connected together in a Y across here. So the lights themselves are going across. Oops, sorry, wrong one there. That's my A phase. A phase going across, B phase going across, and my C phase that is going to be going across as well. And then all three of these are going to go and have a common connection here across the middle, and then we are going to go and tie that down to actual ground over here. Once we've got it tied down to ground, all of my lights over here, if this was a 600 volt system, a 600 volt delta system, you should see that by virtue of these things being connected in a Y across there, that each of my lights would be operating at that 347 volts. So they're going to be glowing somewhat dimly. As soon as we go to a fault on the system, what happens is that one of these points, one of these lines over here, and this is on the actual delta system itself, is now going to go and get brought to the same potential as ground. Remember how we said that everything is floating around that ground. Because it's all floating around that ground, I'm going to see if I can just select just this. No, one second, let me see if I can do the lasso select. Perfect. Because this neutral is normally going to be sitting right in the very middle over here, but as soon as we accidentally ground one of those lines, then this ground or this neutral actually moves over to that point. So if we accidentally ground down my line C, we'll do line C over here, we see that the neutral is going to move over there. One second. The neutral is going to go and move over to that point. And that also means that if that neutral point has moved over there, this neutral point as well is going to be at the same potential. Is there any difference from here to here? Absolutely not. There's 0 volts. Because there's 0 volts across it, that light is going to go out. And because in essence, we've taken this center point over here and we have just grabbed it and bent it up to here, now this light is stretched all the way across from here to here, and this light is stretched all the way across from here to here, which is what makes these two get much brighter. And then this one go dark over here once we get that ground of the system. They show that one over here. Same thing, this line over here and this line, there is 0 potential difference between where the ground fault is on this line and where the actual established ground is there. 0 volts, that thing has gone dark. And because this point is the same as this point, it's the same as if B got stretched directly across to the C line. And because this point is the same as this point, it's the same as if A got stretched directly across to my C line there as well, which is why those two are brighter. Okay, that works the lights. Sometimes what we're going to do, though, is we're going to want to, first of all, control that current if there is going to be a ground fault, and then we want to go and take care of any of our system that's going to be attached to it. And we're going to do that through zigzag transformers. Remember that zigzag that we had? We said that this thing is going to go and be, for us, in a lot of cases, a filter. And that's what this one is over here. It doesn't have a high side. This one is just being connected across into a low side over here. And what we would see is we would see like a and an A together, and a B and a B together, and a C and an A together that we have for the phases that are connected across there. It creates that neutral point inside of there. Normally speaking, we shouldn't have anything that's going to be flowing back through here. Here's the neutral point, and what we've done is we've just taken this neutral point, we put a current limiting resistor across the bottom of it. Then the other thing that we've done is we've taken a alarm relay and we've attached it with a window type of CT. That's one of those CTs that clamps around stuff. That window type of CT over there is going to go and monitor all the lines. Now we know that the net sum of all the currents inside of a delta system is going to be 0. Right? We've seen that before, where we just go and add those phasors together, and they come back to form a value of 0 like that. Which means that if the net amount of current is 0, the net amount of flux is going to be 0, which means that I'm not going to establish any sort of voltage over top of this alarm relay. It's going to be shut off. And my lights as well are also going to be shut off at this point. Under a fault, we're going to go and get some stuff that's going to go and happen, though. Over here, they're showing us that the C line has faulted out. And so because the C line has faulted out, we are going to go and have not all of my current that's going out to the load anymore. Normally, And even with this line faulted, there's still going to be current going out to the load. But there's also now going to be a new current that is going to go and divert because this line is grounded right at that point. This new current is going to go and travel through the bonding system, and it's going to travel up through here. Now, we have placed a resistance in here, so it's not going to be a dead short with unlimited amount of current, because otherwise we would get a massive runoff of current. But what it's doing is, for us, it is now diverting some of this current back around the CT. Remember that the CT only reads 0 when all the current that is going through it in one direction is coming back through it again. Then it would read a net of 0. But as soon as we go into this situation where some of our current is coming through but then circuiting around like that, this thing is now going to go and have a voltage potential across it, which means it is going to go into alarm. So the alarm relay is going to go and fire on at this point. My C line is going to go dark, and my A and my B line are going to go and get brighter. So I know which line it is that faulted. I've got an alarm relay that fires on. A C line has gone dark, my A and my B line have gone back to being bright, and the actual current itself is now being diverted and controlled through this current limiting resistor, or what we would call an impedance that we have across there. Allows us to go and track down faults really, really easily because we know exactly which line it is. After that, there's going to be, some equipment called pulsers and stuff like that that you're going to use on these systems to track through that. It's going to put a pulsing current onto it, and you just look for where the current stops. High voltage systems, as we said before, high voltage systems are oftentimes going to go and get used for distribution, because we can get away with only a tiny amount of current to transfer all of our power out and around. But they do have a issue in that we can't just go and place lights across it, because if the light burns out, we would have to open, it would have to be a high voltage light. It's just a lot of work for us to try and sort stuff out like that. So what we'll often do is we will go and use our PTs. Over here, I've got my high voltage lines. Let's go and say that this is 25,000 volts. If this is 25,000 volts, I see that I have got a PT that's connected across, and then I'm forming a star point, a neutral point with that one over there. What we're going to go and have is we're going to go and have phase value of voltage across here, so I don't have to insulate as high. It's going to be 14.4 kV that we're going to see across there. And then on the other side of that, my PT is going to be a 14.4 kV to 120 volts. It's going to go and place at 120 volts. And what I see on the other side now as well is that I've got 120 volts, but I've got a connection that is now being made in a delta configuration. Disregard these little lights that you see right now, okay? The lights that we see, we can ignore them, but if I follow this line through, I see that A goes to B, B goes through to C, C goes through, and all the way back to A, like that we are going to go and have across it. And normally, what I'm going to go and have, if I take a look at this alarm relay is basically taking the place. It's the connection between my A and between my C. So it's the same as if my current was coming from here to here to here. So this alarm relay is being placed right across this point over here, which should be a net of 0 there. So I'm going to go and have really a net difference of 0 volts that's going to be placed across there. Each of these lights is being placed across the delta connected phases that we are going to go and have here. So this light is going to be connected basically in parallel. This one is going to be connected in parallel, and this one is going to be connected in parallel across there as well. And so as long as each of my phases up top is good, each of these phases should also go and be good. Those lights should be lit. Let's just erase some of this, and we'll go into the lights being lit. So lines are good here right now. So I've got 0 volts across the alarm relay, and I have got absolutely all of my lights themselves that are going to go and be lit. As soon as I go and ground down one of my lines, that grounding down of the line itself is going to go and short out to this grounded point, this grounded Y. And remember, instead of us having lights across the center, now we have got PTs that are across the center. So instead of a light going out, we're going to go and have a PT that is going to go out instead. So what we end up with, if we lose our C type of PT over here, is now we're going to go and end up with a voltage differential going across from here to here. This alarm relay is going to go and sound, Because there is no voltage across here, this light is also going to go out at that point. We're going to get an alarm that's going to sound and a light that is going to go across there. The other two lights are actually going to go and increase, because if this over here has gone and dropped away to 0, closing this one off, these two are going to go from 14.4 kV. They're now going to go and make that jump all the way up to 25,000. 25 kV. So we need to make sure that they're rated to go and handle that. When they jump up, this value of voltage that we had on our secondary is also going to go and jump up. Okay, that's it for all of our instrument transformer connections. There's a lot to process inside of this one once again, but it is, once again, it's just relying on the fact that you understand what we've covered off inside of our earlier transformer connections. Go back, you've got all the videos, look through stuff, in the Q&A sessions, make sure that you're asking the questions if you need them.